Hi students, in this video we are going to learn the experiment number 7 of the mechatronics subject having title PID control of mechanical system using suitable simulation software. Actually this is the first part of the experiment, the second part will be uploaded soon. First of all, before studying the PID controller, we will see on-off controller. On-off controller is installed in a you can install this system as well in your room where there are some terminologies. Set point, process variables. Set point is the temperature where we have to maintain the temperature of the system. Suppose 70 degree Fahrenheit is the set point, and process variables are the temperature which is varying. It can be, see, this graph, y-axis graph shows the process variable. Here process variable is temperature, and this is the set point. Now see, here the room temperature has to be maintained at 70 degrees Fahrenheit, but we are giving some margin for the heater to work, because the in room the 2 degree centigrade difference will not affect the room occupants, or room means the margin is given as 68 to 72 here. Now see, I will explain this working from this graph. Initially, when the temperature is below 70 degree Fahrenheit, then the heater is kept in the on position. Okay, and once the temperature reaches above 70 degree Fahrenheit to 72, the heater will be in off position. Again, this continues till the temperature falls from 72 to 70, and once it reaches here, again the temperature means once it is going below the 70 degree Fahrenheit to 68 degree Celsius, 68 degree Fahrenheit, sorry, 70 to 68 degree Fahrenheit, then the heater is on position. Okay, heater is kept in on position. Like this, continuous on off position, the heater is kept and the system will work. This system is suitable in the household, but it is not useful in the industries. What the industries want? The industries in the industries want the smooth curve. Okay, suppose draw like this curve, or like this curve is required for the industrial work. Okay, but here the curve is like this. This is not suited to the industrial work or where there is high precision is required. To have this kind of operation, to have this kind of purpose of PID control, here here the aim of the PID control system is to, the system should be maintained close to the desired value regardless of the disturbance. This is the main aim of the PID control system. What is PID? PID stands for proportional integral derivative. Proportional integral derivative. You see, this is the block diagram for the system. proportional integral set PID control system is used here, and this is the set point or input point, and this is the feedback path. This shows the feedback path, and this is the difference between the set point and process variable is termed as error. Okay, the term as error, and that error is transferred to the PID system, and we will get the desired value in the output. And depends upon the here actually what we are doing, we are changing the value of now here proportionality gain in the proportional controller, or integral gain in the integral controller, or derivative gain in the derivative controller to a one suitable value, so that we should get the ideal curve like this. Okay, that values of Kp, Ki, Kd we have to find out by using trial and error. Okay, we have to find by using trial and error. Okay, we have to find by using trial and error, so that the system will work smoothly. Okay, instead of using all the three control, you can use only one control, P control or I control or derivative control. Okay, but what are the drawbacks of using only one control system, that we will see now. Okay, see here, this is again another block diagram where some equations are shown here. Proportional controller means here it is multiplying the error by Kp constant. In I integral controller, it is taking the integral of the error over a period of time, and at the same time multiplying by Ki constant. And here in derivative integral, it is taking the derivative of error signal with respect to time, and at the same time multiplying by Kd damper coefficient. Okay, and all are summed up here and transferred to the plant. Okay, now this is some terminologies are there. Again, some we'll see: set point, process variable, and this is the for P control response, and here the steady state error. Here the oscillations are reduced. Here oscillations are reduced, and after certain time this line is getting continuous. Okay, this line is continued like this. Okay, and this is continued, this is our set point. Means there will be continuously the difference of this much distance, and the difference will be there, and that is called as a steady state error. Steady state error, and that steady state error is present in the P control system if you alone use only P control. Okay, only if you alone use P control, when you singly use P control, then there will be the steady state error, and that we have to remove. That is our target. Okay, now again here are some terminologies are there. This is the rise time. This shows the rise time, the time required to rise from initial to the steady state, and this is the peak, and this is the overshoot, means the value above the set point is overshoot, and value below the set point is undershoot. Okay, and this is the settling time. This much is the settling time. Okay, this much is the settling time. Some terminologies are there. Now, to understand clearly what is the effect of Kp, Ki, Kd on the working of the mechanical system, we will see one video so that your concepts will be clear. This video you can also download from YouTube. Actually, I have used this YouTube video. Now see here, you will see its from start. Watch it from start. See, this is the pointer, this is the motor, and here this is the PID control. The motor is working on PID control. Initially the power is off and the operator is rotating manually the pointer. Now see, initially the only Kp value is taken, that is 200, and Kd and Ki values are taken as 0. Okay, and see, this is the desired position. It is the operator is giving some angular displacement to the pointer, and we will see its effect of Kp on the movement of the pointer now. Now see here, see, there is some steady state error. Instead of going to the set point, it is going some away from the set point. That is nothing but the steady state error. Again, see the video clearly now. I will not pause now. The set point, the angular displacement given by the operator. Now see, okay, it is going from this position to this position. Means this is oscillating. This is called as oscillating, going from here to here. Okay, hence it is oscillating, and as well as overshoot. Overshoot means it is going above the set point. Okay, it is going above the set point. Okay, it is going from here to here, is oscillating, and again without going to the mean position, it is going above the set point, that is the overshoot. Okay, now the Kp is increased to 500, and we will see the effect. Now what it has told, it has less steady state error, but it oscillates a lot. See, it has started from here and reached this position, again come here, and it has oscillated now. Okay, means oscillation has increased. See again, 500, Kp 500, started from here and here, and here it has reached to this position. Now he is using Kp as 1000. Okay, see, the oscillations are increased too much. Oscillations are increased. Okay, though there is some steady state error is there, the oscillations will be there. Okay, oscillations will be there. Okay, now to avoid the oscillations, they are using the derivative gain. Clearly here it is mentioned, to damp the oscillations they are using the derivative gain, and also reduce the proportional gain a little. Okay, means instead of using 1000, we can use 500 here, and we are damping the oscillations. Clearly you can see here, see, it has damped to oscillation. Oscillations are not present now. Okay, clearly see, oscillations are not present. Okay, but there is some error. There is some error because it has not reached to this position. Okay, there is some error. Okay, now there is some steady state error. How to get rid of that steady state error, it is mentioning. Then for that we have to use the Ki. Okay, for that we have to use the Ki. Now again it is using proportionality controller and proportional integral controller, and KD is kept as 0 here, and KP value it has reduced now from 500 to 400, and KI is 400. Then see, KP is there, means it is having some vibrations will be there, or sorry, oscillations will be there, and Ki 400 means here we are not using damper now. Damper we are not using means here and see the effect. Okay, it is reaching to the, but somewhat what it is mentioning, the key here is that this is a real system and not ideal one. For ideal one it will reach to the mean value, and to fix to the means to avoid the steady state error we need to anti-wind up the code. That is not required for us. Just remember, when you use all these three, control, we are achieving our goal. But see, here we are using the different values of KP, KI, KD. Initially 200 of for KP we have used 200, then 500, then 1000, then 400, then here 300, 400, then 25 like that. Okay, and these values varies from system to system, and we have to find the correct values of this KP, KI, KD, and that is found out by using trial and error method. Okay, trial and error method. Okay, and in this way the system can be controlled. System can be controlled. Okay, now again we will read out this slide. I will read out this slide. When you increase the KP value, oscillation increase, improves the rise time. When you increase the KI value, reduce the steady state error, and when you increase the KD value, it dams the oscillation. Same thing is explained in this graph. Okay, this much is sufficient for the first part. The second part, simulation by using MATLAB simulation software, will be explained later. Okay, thank you very much from this video.